Hello students, welcome to EPG Pathshala. I am Dr. Rajesh Ghangal from Manav Rachna International University. Today we are going to talk on a module Gas Liquid Chromatography, Universal and Selective Detectors under the paper Chromatographic Techniques. After completing this module, you should be able to learn about the various types of detectors used in the gas chromatography, to gain knowledge on gas chromatography detectors that give univariate and multivariate signals, to understand the basic principle and instrumentation of different types of gas chromatography detectors, to study the specificity and selectivity of different types of gas chromatography detectors, to understand the basis of selection of detectors for various applications. Gas chromatography is a method of choice over other chromatographic techniques due to its detection system or the detectors. Carrier gases used in gas chromatography are transparent, due to which the background level and the interferences are quite low in gas chromatography detectors. The detection limit is the minimum quantity of analyte that can be distinguished from the background. It's the ability of the detector to differentiate signals from the eluting compounds to that of the signal from the neighboring background noise. Numerically, it can be measured as a signal to noise ratio. Larger this ratio for a given amount of solute in a given set of conditions, better is the detector, as it would be helpful in detecting minute quantity of the solute. Noise can originate from many sources, like due to the events of detection process, thermal and vibrations, etc. Analog and or digital detector electronics can be used to reduce high frequency noise. It is the discrete choice of the designer as to how much filtering is needed in analog and digital sections of the signal processing circuit. A middle path is looked upon to balance detector response time and noise suppression. Major source of noise in most analysis is because of the chemical noise and is considered as a low frequency noise. Detectors can be classified on the basis of signal they produce. Examples of detector that give single signals are thermal conductivity detector, flame ionization detector, alkali bead or nitrogen phosphorus detector, flame photometric detector. Examples of detectors that give multiple signals are atomic emission detector, infrared detector, and mass spectrometer. On the basis of compounds being detected, gas chromatography detectors can be of two types, universal and selective. As the name suggests, universal detector can detect almost all the types of compounds that elute out in the process. For example, thermal conductivity detector and flame ionization detector. While selective detectors are able to detect a single characteristic of interest while ignoring everything else. Selective detectors detect only a specific class of compounds based on physical, molecular, or elemental properties. Examples are nitrogen phosphorus detector and flame photometric detector. Detectors can also be classified on the basis whether it responds to the mass flow of the annihilate passing through it or to the concentration of annihilate passing through it. In concentration sensitive detector, a signal will be generated which will be proportional to the annihilate concentration in the carrier gas as it passes through. Example is thermal conductivity detector that gives result in concentration terms like nanogram per milliliter. On contrary, mass sensitive detector signals the mass of annihilate passing through the detector in a given time. For example, flame ionization detector that gives a result in mass per time, that is picogram per second. The properties of the detector are sensitivity and specificity. Sensitivity of the detector is to measure the change in response to change in solute amount or concentration. Higher the sensitivity, better one can differentiate between two small changes in annihilate compounds. Specificity, on the other hand, is the ability of detector to detect a specific atom or functionality present in the annihilate. Thermal conductivity detector. It is a non-destructive universal detector which is most commonly used for the analysis of light and permanent gases. Although it is one of the least sensitive gas chromatography detector, but due to the advantages like it has wide linear dynamic range, requires little power and no fuel gas, and has no flame and is expensive. Thermal conductivity detector is a popular detector and sometimes the only choice for few applications. Thermal conductivity detector can be used in portable micro gas chromatographs as it can be easily miniaturized and run on low power consumption. Thermal conductivity detector integrates Whitestone bridge circuit and measures change in resistance of heated filament as the sample passes through. Column effluent containing separated annihilate flows over one filament, that is termed as sample column, and the clean carrier gas passes over the other, that is termed as reference column. The idea of introducing a reference column in original thermal conductivity detector designs was basically to cancel baseline rises which occurs due to stationary phase bleed through the run. For that, an identical column was attached to reference side with same column flow as that of analytical side, assuming that both the column would bleed same and would cancel the signal rise due to the stationary phase bleed on the analytical side. Due to advancements in column technology and stationary phase, the problem of stationary phase bleed is now not the major factor for using a column in reference side. As compared to other gas chromatography detectors, thermal conductivity detectors are more sensitive to temperature variation. Thus, the function of reference side of the thermal conductivity detector nowadays is to minimize the drift due to temperature and flow change in the cell during the run. Let us study about the principle on which thermal conductivity detector works. Thermal conductivity is basically a physical property of a molecule that signifies its ability to conduct heat. Carrier gases used in gas chromatography have high thermal conductivity, thereby helping to drain heat away from the heated filament. As the eluted solute passes over the detector's sample filament named channel 1, its temperature will rise relative to the reference filament, that is channel number 2. Because the annihilates have low thermal conductivity and are less efficient in draining the heat away, this in turn will increase the temperature in the sample filament, that is the channel number 1. Therefore, the signal is a function of solute concentration and its thermal conductivity relative to that of the carrier gas. Keeping this principle in mind, a researcher should use a carrier gas having a different thermal conductivity to that of the lowest annihilate concentration in the sample, which is to be obtained highest sensitivity from the thermal conductivity detector. To minimize problems such as detector contamination, solute condensation, and peak tailing, the detector should be operated at a temperature that equals isothermal column temperature. Other precautions include like high temperature should be avoided because sensitivity of the detector decreases at higher temperatures. With usage, life of the detector filament do decrease and eventually burn out with time. Use of thermal conductivity detector at high temperature decreases its lifetime also. Lifetime of the thermal conductivity detector also depends on corrosiveness of gases being analyzed and the exposure to the vibration or the shocks. We will now study about the next universal detector, that is flame ionization detector, FID. Flame ionization detector is the premier detector in gas chromatography. It has some unique properties and performance that puts it above and beyond all other general used detectors in gas chromatography. It is a destructive mass sensitive detector, which means that its response is proportional to the mass of carbon that passes through it in unit time. In this regard, flame ionization detector response is stated in terms of picogram carbons per seconds, and the detection limits of flame ionization detector are as low as picogram carbon per second. Unit carbon response means that flame ionization detector responds linearly to the mass of carbon flowing through it independent of compound structure. The flame ionization detector gives a unit response for most hydrocarbons within a couple percentage error. This attribute of unit carbon response allows one to quantify components in a mixtures without having calibration standards for every component. This detector is useful when estimating concentration levels of components in a sample when identities are unknown or when the standards are not available for calibration. Quantity of components in a sample will be proportional to their peak areas. So, a simple area percent report will fairly closely reflect the mass percent of each component in a mixture. This is extremely useful when analyzing complex samples such as those in the petroleum industry, wherein samples can contain well over 1000 components. The unique attributes of flame ionization detector are unit carbon response and wide linear operating range, that is up to 7 orders of magnitude. When combined with its other attributes such as low cost, ease of use, speed of response, and ruggedness, it is not surprising why the flame ionization detector is the premier univariate detector of choice among the gas chromatography. This slide shows the schematic representation of a flame ionization detector. The eluent exits the gas chromatograph column designated as A and enters the flame ionization detector's oven, that is B. The oven makes sure that as soon as the eluent exits the gas chromatogram column, it does not come out of the gaseous phase and deposit on the interface between the column and the detector. This deposition would result in loss of effluent and errors in detection. As the effluent travels up to the detector, it is first mixed with the hydrogen fuel, which is represented as C, and then with the oxidant, that is represented as D. This oxidant mixture continues to travel up to the nozzle head where a positive bias voltage exists, that is designated as E. This positive bias helps to repel the reduced carbon ions created by the flame, that is F, pyrolizing the eluent. The ions are repelled up towards the collector plate, which are connected to a very sensitive ammeter, which detects the ion hitting the plates, then feeds that signal, which is being generated at H, to an amplifier, integrator and display system. The products of the flame are finally vented out of the detector through an exhaust port, which is designated as J. An excess flow of air is required to ensure complete combustion, unit carbon response, and a widest linear dynamic range. In general, a ratio of at least 6:1 of air to hydrogen has empirically been found necessary to achieve the widest dynamic range possible with this detector. The next detector would be studying about is electron capture detector. It is non-destructive, concentration sensitive, and is most sensitive non-hyphenated gas chromatography detector. Electron capture detector is a detector of choice for many environmental gas chromatographic methods due to its inherent sensitivity and selectivity for halogenated compounds. Due to its unique attributes, the electron capture detector allows low-level analysis of chlorinated pesticides to perform on routine cost-effective basis. Looking at the principle of electron capture detector, an electron plasma is established in the detector through the ionization of a continuously fed reagent gas of relatively low ionization potential such as nitrogen or a few % of methane in helium. Beta particles emitted from a radioactive source are used to ionize the reagent gas, releasing electrons and sustaining the plasma. Typically, radioactive sources such as nickel and hydrogen are used. The resulting background abundance of electron is measured usually by using a pulse circuit with 30 to 50 volt pulse. During each pulse, the background of electrons is completely collected and the current is measured. The plasma quickly re-establishes at the conclusion of each pulse. One approach in electronics of electron capture detector is to integrate the current measured during the pulse and the output of the result as a continuous DC signal. The alkali bead detector, also known as thermionic ionization detector, is also commonly known as nitrogen phosphorus detector. This detector is highly selective, destructive detector that finds wide use in food, flavor, forensics, and pharmaceutical and pesticide analysis applications. Most modern nitrogen phosphorus detectors are based on a heated bead design described by Kolb and Bischoff. Response of the nitrogen phosphorus detector is generally thought to rely on a selective moderated surface reaction between nitrogen or phosphorus containing compounds and certain alkali atoms in a cool plasma. Salts of rubidium and cesium have been used successfully for both nitrogen and phosphorus selective detection. Salts of these alkali metals can be either coated onto or integrated into ceramic or glass beads that are in turn attached onto a wire that is used to heat them. Now, looking at the working of nitrogen phosphorus detector, column effluent mixes with a few milliliter per minutes of hydrogen and a few hundred milliliter per minute of air as it leaves the detector jet. With the low flow of hydrogen, there is actually no flame at the tip of the detector jet. It is important to keep the bead cool for maximum sensitivity, especially for nitrogen containing compounds. A flame would overheat the bead, causing similar problems as running the bead with too much of current. Without a flame, hydrogen is combusted just at the surface of the heated bead, forming a localized plasma wherein alkali salt in the bead are reduced or neutralized and are evaporated so that the reduced alkali metals can then catalytically react with nitrogen and phosphorus containing compounds. These ions are then attracted to and collected by a collector electrode that is held at a few hundred volts relative to the jet. As the alkali metals are depleted from the surface, they are replenished from the bulk of the bead or coating material. There are many variables associated with the response of nitrogen phosphorus detector that conspire to yield a different sensitivity, selectivity, and lifetime based on bead type and operating conditions, such as characteristics of the bead, the bulk composition, size, porosity, nature, and concentration of the alkali salt. Next variable is the operating variable, which includes bead temperature related to the bead current, air hydrogen gas ratio, detector temperature, carrier gas, and makeup gas flow rates. Detector design also is a variable where voltage biasness on the collector electrode and proximity of the jet to the bead surface. Bead history such as age, exposure to poison, and maximum temperature. So these are the basically variables which are associated with nitrogen phosphorus detector. Flame photometric detector is a selective and a destructive detector. It is a destructive detector that uses a flame, but instead of measuring the ions from one process to another, it measures the light emitted from phosphorus or sulfur combustion product. It is a popular selective detector used, among other things, for a specific detection of sulfur in petroleum and petrochemical samples, and for the specific detection of phosphorus containing pesticides in food and the environment. Now we will study about the principle on which flame photometric detector is based. During the combustion process of organic molecules in a hydrogen flame, many different forms of excited fragments and recombination products are formed. When these excited ions recombine and relax into a stable form, they emit light. The spectral and temporal characteristics of the emission are species specific and can be exploited for selective detection. Typically, The excited species that emit light include those from the carbon, oxygen, phosphorus, and sulfur. Typically, the flame photometric detector designs monitor emission using a photomultiplier tube, which is positioned above the flame, that is in a cool region where combination and emission occurs. An optical notch filter is positioned between the emission zone and the photomultiplier tube to select a narrow wavelength region corresponding to where the sulfur or phosphorus emission is highest relative to background, usually being carbon emission. Filters of around 395 nanometer for sulfur and 525 nanometer for phosphorus are typically used. To measure both sulfur and phosphorus simultaneously, dual detector designs are also used with two filter photomultiplier tube combinations. Now we will learn about photoionization detectors, that is PIDs. Photoionization detector is a non-destructive, partially selective and concentration sensitive. Since the photoionization detector is a non-destructive, it can be used effectively in a series with other detectors of the gas chromatography. It has no flame and fairly simple, safe and rugged, and it can be effectively integrated into portable gas chromatographs for field use. It is often the detector of choice for trace level of aromatic compounds of environmental and health concern. Photoionization detectors are based on principles and instrumentation as discussed below. It creates a molecular ions using high energy photons from a sealed light source. Even though strong enough of ionized molecule, the energy from the lamp usually does not cause molecules to fragment. The molecular ions are attracted to a cathode and are neutralized, yielding in a original intact molecule. The current resulting from neutralization is measured and represents the detector signal, and this current is proportional to the number of ions neutralized, which in turn proportional to the concentration of the compound in the cell. The next selective detector which we will study is electrolyte conductivity detector, that is ELCD. The electrolyte conductivity detector is a destructive, mass-sensitive, selective detector. Its main use is for regulated methods designed for selective detection of halogen-containing compounds. Electrolytic conductivity detector consists of three principal components. First, the reactor assembly, the cell solvent assembly, and the detector controller. Although the principal mode of operation of electrolytic conductivity detector is the halogen mode, however, sulfur and nitrogen modes are also possible. Each detection mode requires a specific reactor, resin cartridge, and solvent. The electrolytic conductivity detector can be used as a standalone detector or in tandem following a photoionization detector or any other destructive, non-destructive detector. Now coming on to the working of electrolytic conductivity detector, it converts eluting compound with the target heteroatom like halogens, sulfur or nitrogen to an ionizable gas using a reductive conditions at a high temperature ranging from 800 to 1100 degrees centigrade in a catalytic microreactor. The gaseous reaction product continue to the detector cell where they quickly dissolve in a flowing deionized solvent stream, thereby increasing its electrolytic conductivity. A simple conductivity detector amplifies the change in conductivity and produces a signal that is proportional to the mass of the target species. The solvent stream then flows through a deionizing resin bed and filter as it is continuously recycled. High levels of hydrocarbon solvents cause elemental carbon buildup in the reaction tube under certain conditions, thereby decreasing the performance of the detector and require more frequent maintenance. To prevent detector overload by high amount of solvent venting is done by time program controlled of using a vent valve. In the end, we can summarize what all we studied today in the following points. We learned about the various types of detector used in the gas chromatography. We classified gas chromatography detectors on the basis of univariate and multivariate signals. We looked upon the basic principle and instrumentation of different types of gas chromatography detectors. We also studied the specificity and selectivity of different types of gas chromatography detectors. In the end, we also learned the basis of selection of detectors for various applications. Thank you.